Hello, everyone. I'm Su Hua, the President of Greater China Region of Infineon Technologies. First of all, I would like to take this opportunity to thank the two organizers of this event, Taiwan and the Honghai Research Institute. Indeed, it's a great honor to be invited and to share the common platform with the distinguished Nobel Prize laureate and distinguished industrial veterans. We are facing several macro challenges in today's environment. Climate change, natural resource shortage, urbanization, and digitalization are the major ones among them. As a result, we all need to work together more closely and promote the energy efficiency through the innovation of materials and technology. The topic of compound semiconductor in e-vehicle is a very important and a relevant one in today's discussion. According to the recent report from Omedia, silicon carbide and gallium nitride power semiconductor 2020, the third generation power semiconductor market with the silicon carbide and gallium nitride is expected to surpass the $1 billion mark in 2021 from $571 million in 2018, mainly due to the demand for hybrid and electric vehicles, power, and photovoltaic inverters. Silicon materials have the highest technical maturity and advantages in cost performance at a device level, so it will remain the main device material in various power semiconductors in the future. Both silicon carbide and gallium nitride can achieve higher efficiency with a smaller size through higher conversion efficiency and a lower power loss than silicon. In particular, the temperature stability of silicon carbide has been proven in the market. With the future trend of energy saving, emission reduction, and green environment protection, the development of compound semi-materials will be accelerated towards higher efficiency and reliability, both technically and economically. Infineon is the worldwide leading manufacturer of power semiconductors. Energy efficiency, e-mobility, and IoT are the main drivers and focused area for our future business growth. In the automotive industry, many OEMs have announced billions of dollars worth of investment in EVs as they are facing strict regulation on CO2 emission in many markets around the world. Infineon has more than 20 years of experience in silicon carbide technology. The percentage of silicon carbide-based semiconductor components for EVs will be increased to 30% by 2025. Obviously, there are two major benefits: reduce the loss of the vehicle power system and increase the efficiency. As Infineon, we have delivered the first frame-based silicon carbide module to the market. We also offer the optimal choice of technology for EV traction inverters, hybrid pack drive IGBT for front axle, and both hybrid pack drive and cool-SiC MOSFET can be used for rear axle. If an OEM increases the efficiency target, or if the required voltage level rises, cool-SiC MOSFET will become the preferred device. We have demonstrated that the fine-tuned silicon carbide trench technology outperforms planar technology. Instead of pushing full potential of the performance, Infineon turns this budget into much higher reliability. In addition to the power semiconductors, Infineon offers full system solutions addressing all EV segments by using our automotive-grade microcontrollers drivers, as well as different types of sensors. Infineon has invested in additional capacity while ensuring the performance, quality, and the reliability of its own silicon carbide products. In Villach, Austria, for example, a new 1.6 billion euro plant is about to open to produce power semiconductors for hybrid and electric cars. Nevertheless, silicon carbide will not simply replace silicon devices. Both technologies will coexist in the EV arena, depend upon the individual requirements from an OEM on a specific application. Infineon offers a comprehensive product portfolio covering all power technologies, silicon, silicon carbide, and gallium nitride. We provide fuel-efficient solutions that enables the electrification of vehicles and help our customers around the world to grow their business. Compound semiconductor in e-vehicle is always an exciting topic to Infineon and myself. It's really a great pleasure to join this virtual forum, and I'm looking forward to the future opportunities to meeting everyone again in person. Thank you.
Ladies and gentlemen, welcome. Welcome to attend the next forum, Compound Semiconductor in Electrical Vehicle. I'm Hsiao-Chin Tuan, Senior Director of Analog Power Specialty Technology of R&D in TSMC. Talking about 3.5 semiconductor technology, there are silicon carbide and gallium nitride on the horizon. Silicon carbide provides voltage higher than 1000 volt and power higher than 10 kilowatt, which are applicable in electrical vehicle, rail traction, power grid, and the windmills. On the other hand, gallium nitride provides solutions for less than 1000 volt and power delivery typically lower than 100 kilowatt. As we TSMC evaluated the two technologies back 12 years ago, we didn't think silicon carbide a good fit to our business and our technology. So we have a focus on the gallium nitride on silicon technology only. 12 years passed by. There have been a lot of progress in both silicon carbide and gallium nitride. Silicon carbide has been moving about 20 years earlier. It began from Schottky barrier diodes. In the recent 5 years, the breakthrough in MOSFET has called more attention to respond to the urges of a green and even greener from all over the world. Today, the key driving force is the electrical vehicles. Gallium nitride has also overcome lots of technical challenges in epi material, device performance, reliability, and manufacturability, etc. The technology started volume production first in consumer products in recent years. For now, it also expands to data center, electrical vehicle, DC-DC power supply in 48-volt system, and the 5G base station. In this year, it's estimated 500 data centers over the world already. It's also estimated more than 6 million electrical vehicles shipped in this year. It's also estimated about 500,000 5G base stations in building. Out of this, the industry provides very good opportunity for both silicon carbide and gallium nitride. From another angle, the world does need cost-effective solutions from both the compound semiconductor technology. I hope everybody to enjoy the inspiring talks arranged by the forum and wish everybody healthy and this event a very big success. Thank you. Thank you very much.
Hello, everybody. Compound semiconductor devices have already been around our daily life. They are all over in smartphones, lighting, display, electrical cars, Wi-Fi, etc. Compound semiconductors will continue to play an even more critical role than ever to provide seamless connectivity in energy saving and for more secured life in future. For compound semiconductors, the utmost important markets and applications are for communication networks, power conversion, solid-state lighting, sensors, and display. In Taiwan, we have an already very well-developed silicon semiconductor ecosystem. We should leverage these given strengths and further extend to compound semiconductor industry and develop a full-blown ecosystem to embrace the enormous market opportunities on next-generation wireless communication, data communication, satellite communication, and electrical vehicle, etc., etc. However, this is such a tremendous effort and can only be done by seamlessly integrating efforts from industry, government, and academia. Compound semiconductor is enabling many innovative applications. It is believed we are still in an early stage for another disruptive growth for compound semiconductor industry. Driven by the mentioned exciting markets, the best is yet to come. We absolutely need to grasp this great opportunity and fully leverage our strengths to repeat Taiwan silicon chips success story onto compound semiconductors. Finally, I wish we have successful forums during the Power and Opto Semiconductor Week. Thank you.
Not too long ago, just a few years ago, in our industry, we all thought that the business of power had come to the final stage of profitable developments. Despite the evolution towards the digital power, products were ultra-commoditized. The planar technology for the MOSFETs was at the over-maturity stage. The superjunction or the trench were approaching the same level, and even the IGBTs had reached the prospects of low profit for any investors. Then the automotive industry started to move towards new energy vehicles, in particular towards the electric vehicles. These required higher efficiency for the traction, for the battery management, and also for the charging stations. The EV enabled in this way the first shift into the third generation semiconductors with the wide adoption of the silicon carbide MOSFET first and the prospect of the gallium nitride at the horizon. While the SiC and the GaN have been enabled by the EVs, we have recently seen a large demand coming from many different sectors of the industry. Power supplies for data centers, industrial motors, UPS, are all rejuvenating systems like factory automation, air conditioners, home appliances in general, that all have now a significant higher efficiency when using the silicon carbide MOSFETs. On the other side, low-voltage systems like LED for street lighting, solar inverters, and battery management systems, not only in cars, are more efficient and faster when using gallium nitride. I am impressed, as an example, by the mobile phone chargers in China that now require 120 watt of power in the same package as a 10-watt charger. The gallium nitride technologies just allow this. And while the connectivity drives the transition to a digital world, I believe the new compounds or the third generation semiconductors are at the same time driving the transition to a more efficient world with new designs for the existing products and new products that previously did not exist, both on Earth and in the air. This industry may therefore expect large returns, with the new materials being a mainstay for the next decades. At ST, we have been investing on the third generation semiconductors with specific R&D activities as well as acquisitions and partnerships. Norstel and Hexagon acquisitions are two examples in silicon carbide and gallium nitride, respectively. Though very important, the power elements are obviously not the only ones in an energy conversion process. Band gap drivers are another important block of the chain that bridges the intelligence of the microcontroller with the power actuators. We offer as well a complete solutions as discrete elements as well as integrated solutions like our master GaN, able to integrate intelligent drivers with power GaN in the same package. We offer the most successful 32-bit platform in the industry that goes under the name of STM32, a micro family that is constantly evolving in its roadmap towards more power of computation like MPU, higher frequency, lower consumption. This platform is supported by an optimal infrastructure of design libraries and tools that make it very attractive to every developer for any application in any environment, be it a university lab or a garage or an R&D center of a large corporation. I started my career long time ago with bipolar transistors driven by a base transformer. Then we moved to medium voltage MOSFETs, 700 volts, with related gate charge designs. Eventually, we are landing onto high voltage MOSFETs, 1500 volts, with band gap drives. It has been a great evolution into a long journey of energy technologies, as some friends here in Taiwan like to call them. I hope you all also enjoy these fantastic achievements, and I hope you all will contribute to this brave new world that eventually addresses the drama of our time, the environment. With that, I wish you a great workshop, and thank you very much.
Good morning, ladies and gentlemen. My name is Mike Sung. I currently serve as CTO at the AWSC in Taiwan. I appreciate the invitation from President Frank Chen, Professor Corp, and the program committee. It's my pleasure to be here and share my perspective on Taiwan's compound semiconductor industry. As many of you know, even during this terrible COVID-19 pandemic period, the global semiconductor shortage is still ongoing. Very aggressive capital expenditure and the capacity expansion plan are in place to fill that gap. Some people may wonder whether all this huge investment are warranted. As a matter of fact, market always has its ups and downs, but fortunately, the overall market dynamics seems to be supporting this continuous growth, especially for the compound semiconductor industry. As we know, power electronics, RF microwave, and optoelectronics are the three key growth areas in our CS industry. On the power electronics side, the upcoming global requirement for the net zero carbon emission really accelerate the adoption of electrical vehicles. The next generation electrical vehicle will call for more highly efficient power electronics. So wide bandgap compound semiconductors such as silicon carbide and gallium nitride are the obvious beneficiary. As a matter of fact, as soon as the wide bandgap material, the cost structure of wide bandgap material become more favorable, I believe the production volume of conducting silicon carbide and gallium nitride will grow significantly. For the RF microwave, there's an unstoppable trend for people to have the capability connecting to all our surrounding services and infrastructure at any time, anywhere. The need for this ubiquitous connectivity demands tremendous bandwidth to handle such a ever-increasing amount of data traffic. More and more 5G base station and the data center are built to meet that demand. As we know, RF gallium nitride plays a critical role for the fast deployment of 5G base stations. Many people have invested in the RF GaN and hope to capture this tremendous market opportunity. On the optoelectronic side, besides high volume LEDs, the VCSEL or surface emitting laser for facial recognition, 3D sensing, and AR, VR applications really changed the entire ballgame. Unprecedented volume of VCSEL have been fabricated during the past few years. As we can see, all three growth engines of the compound semiconductor industry are really on fire and ready to go. In addition to the market tailwind, Taiwan's compound semiconductor industry actually has another pretty unique competitive advantage. Actually, we need to thanks to TSMC. Taiwan not only has many semiconductor-related raw material suppliers and infrastructure in place locally, but Taiwan also fostered many high-quality semiconductor engineers during the past 30 years. By taking advantage of these invaluable resources and assets, Wang Semi and the AWSC have the opportunity to quickly become the two largest pure-play compound semiconductor foundry company in the world. However, I would like to point out, today Wang Semi and the AWSC still heavily rely on the old-fashioned gallium arsenide as our bread and butter. The highly anticipated wide bandgap material still in an international IDM-dominated playground, especially in the RF microwave area. To change that status quo and have more people and companies in Taiwan to participate in this global wide bandgap revolution, we may need to see more resources and support from local industrial leaders to create a wide bandgap specific supply chain with proper cost structure and eventually a sustainable ecosystem. That way, we may be able to follow the history of gallium arsenide and transform the wide bandgap related product portfolio from an IDM dominated model to our desired foundry based model. Thank you for your attention.